Alright, so for this problem we're going to have to solve the delta G naught when aluminum metal is dropped into hydrochloric acid. So we have a redox reaction taking place, and we're going to be able to find the essentially electromotive force between the two reactants in this case, and use that to convert to a delta G naught. It's going to tell us both whether it is a spontaneous or a non-spontaneous reaction, which we'll be able to figure out anyways from the table, and it's also going to give us an idea of the value for delta G naught in terms of kilojoules. So first thing we need to do is sort of figure out what we're dealing with. So we're looking at aluminum metal, Al solid, and hydrochloric acid, HCl aqueous, and when we dissolve that, it's really going to be H plus and Cl minus. Okay, so these are really the three things here that we have floating around that we need to figure out for the reaction. So what we're going to do is we're going to go ahead and go to the standard reduction potential table, and we're going to look up those three and figure out where they are in relation to each other and what can happen. Alright, so we're at the standard reduction potential, and you remember we're looking for a couple things here. The first one is chloride ion, so the reaction is right here with chlorine, and what I usually just do is, in this case we're going to use the full table. Sometimes you can just write a small table, put the three reactions in order, circle what you have, and then take a look from there. So we have Cl minus, we know, and we're going to go down, and the next reaction that we're going to find that's relevant is going to be H plus. We have that. Note some of these other ones have H plus as well. Here's one, sulfur plus H plus. We don't have the sulfur, so we don't really need to worry about that reaction. Then the last thing we're going to have will be aluminum solid, okay, way down there. Remember from looking at the table and figuring out what you need to do with it, that the higher up, the more likely to be reduced. Well, the chloride, if we look, is the highest up. It's the most likely to be reduced, but it already is reduced, so we don't really have to worry about this reaction. Okay, it's already got its electrons. If we go down to the next one, the H plus, you could see that H plus wants to form H2 gas, and it's in its oxidized form, so this could react to form H2 gas as long as we have something to give it electrons. And if we look down, we can see that aluminum is currently in its reduced form, and it's below, so it is going to go and react and be oxidized to form Al3+ at the same time, and therefore we're going to end up with a reaction taking place. So this is a spontaneous reaction, and if we wanted to write out what the reaction is, we can go ahead and just make some room here. And what we're going to have is we're going to have the hydrogen, the reduction reaction, will be the 2H plus 2 electrons going to H2 gas, and the oxidation reaction, which will be the aluminum solid, okay, since we're going from right to left for this one, to Al3+ plus 3 electrons. Okay, so those are our two reactions. So now when we want to find the E naught of this, E naught of the reaction, it's the standard reduction potential of the reduction reaction minus standard reduction potential of the oxidation reaction. So if we're just using the values on the chart, we're going to say, okay, well, it's 0 volts for the H2 minus negative 1.66 volts for the aluminum, and therefore we end up with a standard reduction for the reaction of electromotive force here of 1.66 volts positive. Now, in some cases you may wonder, why didn't I just flip the sign of the aluminum and make it, when I flip the reaction, make it positive 1.66? You can do that. It then becomes an oxidation potential, and then you can add the reduction in the oxidation potential. I usually just do sort of a cathode minus anode or reduction minus oxidation method, and that way you don't ever have to change the sign. At the simplest level, the way to think about this and to avoid making mistakes is think about this list of numbers here as a number line, and really all you care about is the difference between the two numbers. But if you do write it out, this is the reduction, this is the oxidation, and you were to get the non-spontaneous reaction, when you do the reduction minus oxidation, you would have the smaller number. Like if we did this backwards, it would be negative 1.66 minus 0, and you'd end up with a negative value, which tells you you have a non-spontaneous reaction. Alright, so let's go ahead and turn this into a delta G. Okay, so we can see what we've done so far, and now what we're going to do is we're just going to put this all together and write out one big reaction and convert it. So the first thing we need to do is we need to figure out the overall net reaction taking place here. Okay, if we look at this reduction reaction, we want to multiply this by 3 such that the becomes 6 electrons, and then we multiply the aluminum, the oxidation reaction, by 2 to get 6 electrons on the right, and then we have the same number of electrons being passed back and forth. We can add it together and it will be balanced with regards to the electrons that are getting handed off from the oxidation to the reduction. So when we go ahead and put this all into one, it's going to be 6H plus 6 electrons plus 2 aluminum solid go to 3 H2 gas plus 2 Al 3 plus 6 electrons. So that's now my net reaction, and I can pretty quickly see that we can cancel out the 6 electrons on both sides to get our net. Well, now since we know that delta G naught equals negative N F E naught of the reaction, we can go ahead and start plugging this in. Okay, so our delta G naught will equal negative N is the number of moles of electrons that we've canceled in this reaction, so that's 6 moles. F is the Faraday constant, so that's going to be 96,500 joules per volt mole. And our E, as we found before, is 1.66 volts. Okay, so the volts cancel, the moles cancel, and we are going to be left with joules. In this case, we're going to be left specifically with 9.61 times 10 to the 5th. I'm just going to convert it into kilojoules right now and call it 961 kilojoules. Alright, so 961 kilojoules, sorry, negative 961 kilojoules is our delta G naught. It's a spontaneous reaction, and that's the value of delta G. So that's how you convert from one to the other. Really the only tricky part here is making sure that you find the E correctly, and then knowing how many electrons you're canceling out of both sides when you write that balanced reaction.